I think we're going to continue with chapter 7. We're mostly going to follow chapter 7 linearly up until after the Kramer round lower bound. So if you want to just kind of start perusing through the examples, reading through examples, they'll do a lot of examples that I won't do in class. I'll kind of outline the theory, sprinkle in some examples. So my recommendation for chapter 7 is make sure you know how to do every single one of those examples up through attainment. And so I'll tell you about attainment later. I'm not sure we're going to cover it in depth. Let me just tell you what it is. Sometimes you can come up with a theoretical lower bound on how low you can push an estimator's variance. So let me say it just a little bit more rigorously. With a specified bias level, because there's always going to be some trade-off between the bias and the variance. So with a pre-specified level of bias that you're willing to incur, including 0, so you could say in the class of unbiased estimators, you might in some cases be able to say, here's a theoretical lower bound for how far you can push the variability down. And if you're looking at something like MSE as your metric for comparing things, the bias and the variability are the only two things. And there's a functional form that you can specify for that. I will say that slightly differently again. For every sort of loss function, whether it be squared error loss or absolute loss, there really are only two things that are going on. There's your systematic biases, and then there's how variable that estimator is. Whether or not you can write it down as bias squared plus variance doesn't really matter. It's really only those two things. How much does your estimator fluctuate and how systematically biased is it? So it might be nice to say what's the lowest variability an estimator can take on. Not all problems you can answer that question theoretically. So for certain classes of problems, you can answer that theoretically. And you could probably even say whether or not that bound is attainable. So let me give you a theoretical lower bound on variance. This is Scotland's lower bound on variance, 0. It's totally useless. So -1 would be even more useless. So the question when you come up with bounding theorems is it tight? Or is it attainable and you can actually take on that lower bound? Attainment is basically a backwards engineering of the theorem that tells us what the lower bound is. So the theorem is called Kramer-Rao lower bound, and we won't dissect it enough, I think, to say specifically what the attainment condition is. The way I'll cover it in class is work out the lower bound, come up with your estimator, and work out the variance and see if they match. And if they match, it's attainable. In return for short-circuiting or shortcutting some of that theory, I'm going to tell you about the EM algorithm. So I'm going to give you some practical skills. So anyway, chapter 7, pretty linear all the way through, so start reading through that. I'm going to pause for a moment on the EM algorithm. So they give you an example with it, but I don't think they sufficiently cover it. And I'd like you to have some skills on how to actually do something instead of just a bunch of theory. I'll be giving you a simulation study so that you can actually study the theory that we're going to develop as well. Any questions about all that? Okay, so today we're just going to recap some of the NLE-based stuff. I'm just going to say a little bit about it. Then we're going to go into finite mixture models. I'm going to tell you about the EM algorithm and how it generalizes to other problems, but we'll use it in a specific problem, finite mixture estimation. I'll give you a proof as to why the algorithm works. They don't do that in the book. It's just kind of magical. Here's the EM algorithm, do it. I never really liked that no books had a good proof in it, so we'll cover a proof. And then we'll implement this, and I'll run you a few examples. So today, comments on MLEs. So maximum likelihood estimators, take the likelihood function, maximize it. We'll make a few comments about those estimators. And some caveats. Basically, you need to check the boundaries of things. If you're going to set a derivative equal to 0 and solve, you need to check the boundaries. You need to make sure you have a maximum. The book has a very long-winded way of saying that. So I'll make a few comments about that. We'll make a few comments about Bayes estimators. But basically, they're penalized forms of these sort of estimators. They have something to do with the likelihood. That's at least the most important part of a Bayesian analysis is the likelihood, but they're treating it a little bit differently than what an MLEer would do, in that they want to integrate under the likelihood. And so in order to do that, you need to upgrade the parameters to a random variable via Bayes' theorem, and then you get a whole posterior distribution expressing the uncertainty and a whole collection of possible estimators. So we'll circle back around to these once we get some real decision theory, and we'll build that up after we do the EM algorithm. So just a few comments here, and we'll circle back to these problems when we're describing how good are the estimators that we get out of all of this stuff. So we'll do more comparison. Then we'll move into finite mixture models. We'll recap this. This is just this thing that we saw briefly in the beginning of class. So we studied a problem just like this when we studied the bootstrap. So where I have addition of a whole bunch of distributions where they're weighted. Those weights are positive and these weights sum up to 1. So some of the pi k's, these are just probability weights, sum up to 1, and the pi k's are positive. And I'll put they're greater or equal to 0. Of course, if they're equal to 0, then you probably wouldn't be touching those ones. So it's really a question of what is cap k in all of this. If you knew what cap k is, and you'd probably get rid of those right there. For our context, you get to know what cap k is. So you might have questions at the end. What if this was a real problem and I didn't know what cap k is? So we can have a discussion about that. But there are a whole bunch of techniques on estimating k as well. We'll shortcut that and say you get to know it. For at least all of your examples in your simulation homework. Okay, and then we'll do the EM algorithm. So E stands for expectation, and M stands for maximization. So there's 2 layers to this. There's the implementing the algorithm. And I will say this, we're going to say a lot of theory, we'll derive a bunch of stuff, we'll solve some math problems. At the end of the day, what you code up is relatively simple for estimating these parameters in a finite mixture model. This is also a parameter that needs to be estimated. What are the pi k's and what are the underlying parameters that define the distributions that generate the data? So we need a bunch of math, understand why this works, and then we need to be able to implement it. So I would say the math is really easy, or the math is, we have to think a little bit. The implementation of this shouldn't be something that you're sweating over. It's going to be straightforward and pretty simple to code up. Okay, it's an iterative algorithm, and I'll tell you exactly what it is that you're coding up, and the small things that I don't work through in detail with you, I'll just ask you to supplement that. Hopefully you'll understand that. My experience is usually it takes people 2 times to see this to fully understand it and digest it. So if you're able to kind of understand where you're at with this thing and implement it, I would say that's pretty good, and then you'll want to come back around and restudy all those steps again, what you actually did and why this thing works. Okay, that's it. Any questions about where we're going? Okay, MLEs, maths likelihood estimators. So what you do Step one, form the likelihood. So if everything is IID, it's really easy to form the likelihood of something. So all you do is you write down the product of the little sampling distribution things, and then you conceptualize it as a function of theta. So if xi's are IID, let's say from some distribution fx, given theta, I'm imagining this is high dimensional. So this is just theta 1 out to theta p. Then our likelihood function is going to be proportional to fxi's given theta, cap theta. I goes from 1 to 10. So pretty easy to do in an IID case. This is true for any problem. So write down the sampling distribution and reconceptualize it as a function of your parameter space. So that's a likelihood. Let me give you another example. So a non-IID example. This is the easiest one I can think of. This is called an autoregressive model. So autoregression. Let's say I have something like this. xt, I'll think of t as time, maybe, is equal to alpha plus beta xt minus 1 plus air t. We'll make this really easy. This is normal 0 sigma squared. So it has additive normal air. So this is called an autoregressive 1 model. So what we're doing is we're regressing a future value on its previous value. So this is kind of your basic time series model. Most of your time series models you'll build up out of this. So you could have autoregressive 2 models where we regress not on xt minus, just on xt minus 1, but also on xt minus 2. And you can do that a whole bunch of times. So it's basically a question of how much memory does the process have. You could also have the errors not be independent errors in a model like this. And you could have the errors regress on each other too. So there's memory and residuals. So that's a moving average model. So if you put those things together, it's called an autoregressive moving average model. If you do autoregressive steps, i.e. the mean function autoregresses and the errors autoregress, that's AR and moving average. That's called an ARMA model, if you've ever heard that before. We'll just look at this real quickly just so we can understand how do we build up the likelihood of everything. We need to learn that parameter, probably. We need to learn that parameter, probably, and we need to learn that parameter, probably. I will say this, if beta is greater than 1, this process starts exploding. So imagine this, if xt minus 1 was a 1, this was a 10, or something like that, let's say that was 0. Then this would be 10 plus some air, so let's imagine that was small. So this would be around 10. Then I plug it back in, multiply by 10 again, it becomes something like 100 plus some air, so something around 100, and that's the new value. I plug that in again and I auto-regress again and it jumps up to like 1,000, so it starts exploding. So there are conditions on whether or not you can do the estimation depending on what beta is. So beta has to be a number between -1 and 1 for this to be stationary for you to do the estimation. Saying that, I can still write down the likelihood regardless of whether or not the process was stationary. So the likelihood looks like this. So I'll say the likelihood for alpha, beta, and sigma squared given all of my data, the x1 all the way up to whatever cap t is. So I'll say t goes from 1 to cap t. So keep in mind, in my notation, there's an x0 in there. You have to start the process somewhere. Just for discussion's sake, the only real difference between what a Bayesian and a non-Bayesian will do is how they treat that first data point. So Bayesian would probably put a prior on it and start the process offset by one step, and then put a prior on the first point. What other people might do instead of doing that is they might build up their analysis and tinker that point and see how sensitive it is to everything. In some sense, the Bayesian is automatically doing that by putting a distribution over it, that they're tinkering with it all in one step. So they're very similar analyses. And if cap t is big, usually doing the Bayesian thing and the non-Bayesian thing work out to be about the same. So if cap t is big. Okay, so the likelihood for everything just looks like this. Proportional to t goes from 1 to cap t, f of xt given xt minus 1. So that's the model right here. So I would say this is equal to f x. I guess this is the part that we use to establish what xt is conditional on xt minus 1. So this is conditioned on xt minus 1, so we should include that in the notation. So we've got alpha, we've got beta, we've got sigma squared. This is the likelihood. So it's still just a product of things. So this is my statement about conditional independence. Everything is conditionally independent. The xt's are conditionally independent, conditioned on having the xt minus 1 and the model parameters. So we just need to build up the conditions on everything, and then we product those things together. So nothing complicated. So I always just look over on the right-hand side and see what I need to know that, and those are the things that I condition on. So this is the likelihood. So in an IID case and in a non-IID case, it's usually just as easy to build up the likelihood functions. Likelihoods are just coming in the form of big products, where we're expressing the conditional independencies. I don't think of this as too different because I usually don't say the x's are independent. I say they're conditionally independent, conditioning on the thetas. So the data is not independent, it's conditionally independent. Okay. This is a little bit different. So the distributions are not identical in every step because xt minus 1 is changing. So the functional form might be identical, but the exact expression is different. So this is non-IID. They're conditionally independent, but not identically distributed at every step. There's this sort of reshift of everything. It's changing the shifting. So working with IID cases and non-IID cases are about the same. They look and feel the same to me. Once I write down the likelihood, I'm in business. And I would say this is true for any inference, regardless of which paradigm I want to work in. Once I have the likelihood, I can move forward. So again, likelihoods, I think, are the driving force of inference. If you do like moments to do your inference and you get good answers, I'd say it's because you probably got them. So, okay. So step 1, form a likelihood. Step 2 for an MLE, maximize that thing. Step 2, I'm going to say hard maximize it. We call that maybe the MLE. This is maybe. You've got to be a little bit more careful. And we need to check, I would say, the endpoints. So the boundaries, to make sure they don't exceed that value, whatever the likelihood is. So you evaluate, check the endpoints, plug them into your likelihood function, and make sure they don't exceed that. Otherwise, the endpoints will define your MLE. We've got a really good example of that uniform 0 theta case, or uniform minus theta to theta. Everything happened on the endpoint of everything. And the derivative wouldn't have been helpful in telling us this. So we have to check more than the derivative to do this sort of thing. So check the endpoints right here. And then we also need to make sure we have a maxima and not a minima. So make sure our optima is a max and not a min. Now that's kind of already subsumed into this, the argmax thing. So what I was thinking about when I was saying this is this might be equivalent. So might be equivalent to doing this sort of thing. Take the likelihood function, give it x, d theta 1, set that thing equal to 0, and then come down here, do this all the way for all of your p partial derivatives, d theta p, set that equal to 0, and solve that system. So when we solve this system, then we're going to check that the thetas that we have in here are equal to theta hat. So that's my notation for that. I solve this system, then I take all my thetas and I make them theta hat. And usually I would say this is MLE. This is the part we need to be a little bit more careful about and check these two things. I would say if you've solved this and you have your maximum, you're done. How do you get your maximum? Very typically it might be a calculus problem. But I will say that's if this function is smooth, so not too wiggly, and doesn't have a whole bunch of jump discontinuities in it. So you would need to check all those jump discontinuities as well. So basically, your first 2 months of your calculus class, all that stuff is still true. So no difference here. The book says a bunch of stuff. They say check eigenvalues of your system if you work in a high-dimensional case. And they say, let's look at a 2-dimensional case and give you a bunch of criteria for everything. Did anybody read through that already? The conditions they tell you to check. So they tell you to check the Hessian matrix and check the eigenvalues of that Hessian matrix. Let me just write down what the book says. The book says to check H, which is the Hessian. What's the Hessian? They teach you what this is, maybe in undergrad or some other version of grad school. I didn't know what it was until I got into grad school. Remember, they were just kind of wheeling this thing around in linear algebra. I go look it up. What is this thing that we're talking about that everybody seems to know something about? What's the Hessian? Second derivative matrix. Yeah, so it just has all the elements of this. So this is going to be a big matrix. And I'll say H, I, J element in here is just going to be the derivative. And very often people put this on the log likelihood scale, but you can put it on the likelihood scale. It doesn't matter if you take a log or if you don't take a log of everything. It's a monotonic function. It's not going to change where the optima are in everything. But I would say these are just going to be the derivatives of the likelihood function x d theta I d theta j. I'll put the 2 up there to denote second derivative. So it's your second derivative matrix. Has all of your mixed partials in there, the off-diagonal elements. And they tell you to check the eigenvalues of this system. So for a two-dimensional case, book says the determinant of H has to be positive, and one eigenvalue has to be negative. What did they just say? This is a two-dimensional specification. So this is specific to 2D. In 3D, the criterion would change. So I don't know exactly why they did this. I think they wanted to do this so they could find the MLE for mu and sigma squared in a normal example. That's as high D as they felt like getting. Just real quickly, what are the MLEs for a normal example? So MLE, mu and sigma squared in a normal. What's mu hat? It's X. Did you work it out or did you just guess? You just knew, yeah. So probably worked it out before. Try to do that. That's in the book. It's not too hard. Take a log first. Makes it really easy. It's like trying to find the optima of a parabola. So it might be, okay. What's this one? Squared.
It's the dot divided by n minus 1. So divided by n.
Divided by n. Yeah. Sum of the xi minus x bar squared n minus 1. Sum goes from 1 to n. You can work that out. If I ask you that on a test, I want you to find the derivative, set everything equal to 0, take derivatives over mu and sigma squared and solve. You could probably do all of that and not even address these two conditions. Because if I know what a normal distribution looks like, I know that it's unimodal. So, and I know that the endpoints aren't a factor. How do you know that? A mathematician would say, you got to prove all that stuff. You're not allowed to know things. I don't feel that way. It would be okay if you didn't check the endpoints in an example like that and just commented that this is an unbounded function right here and I know the tails are coming down. So how do you know that it's maximum and not a minimum? You could do the second derivative test. So that's possible. That's what they taught me to do when I was a freshman in college. And just to be cheeky about it, I never would use it on the test. So, because I just used the first derivative test and I checked to the left-hand side and the right-hand side and make sure that the slope just changed. It went from positive to negative. So I used the intermediate value theorem, if you know what that is. So I guess the mathematician might say, you need to prove the intermediate value theorem, that there's a 0 between the negative and the positive. And I'd go, well, isn't that how numbers work? But a mathematician would say, you don't get to know that. So there's always another layer to this game of what you need to prove and who are you speaking to is usually the criterion for that. So I would say for a normal example, you could probably say, I've looked at this as e to the parabola that's upside down, but it has a negative sign in front of it. And so e to that parabola upside down, the upside down parabola, e doesn't change anything because it's a monotonic function. So it inflects the endpoints, but it doesn't change where the optima is. It's still in the middle, over by where x bar is. So I don't know if you need to check all of these conditions. They would say to check this. Now I said do the second derivative test, maybe, so do that sort of thing. You can do it if you want, if you think the problem warrants it and you don't know for sure that you're in a maximum, you would need to check that. I will say for the uniform example, 0 to theta, if you take a derivative over that, you're going to find that the maximum is on the endpoint, and setting the derivative equal to 0 and solving doesn't help you at all. So you do need to go to the endpoints and check that example. Again, I think just draw the likelihood function and know the likelihood function and refer to your picture, and I'll be okay with that. What are these criteria it's all about?
Local optimal condition.
Yeah, so what does it say? I said something about second derivative. This has something to do with second derivative. What about these two conditions? What is it saying about the other eigenvalue? So it's saying one of them is negative. It's saying the other one is negative too. In this, keep in mind what the determinant is. It's the product of eigenvalues. So if it's going to be positive, then they're both negative. So what it's saying is that your function is negative definite. And that means it's like an upside down, I don't want to say parabola because you have e to the minus and it inflects the endpoints out. But if I take the log of it, then you might be thinking that I have this parabolic model. So it's basically doing a very fancy version of the second derivative test. What you really need to check is that all the eigenvalues are negative. There is something called negative definite, or negative semi-definiteness, and that means there's a 0 eigenvalue in there, and that means there's going to be a ridge in your space, a flat spot. And so the maxima are not going to be unique. But there's still a maximum to the problem. So it's basically saying geometrically that the function has a bump in it. You can maximize that. Your maxima are going to your optima are going to correspond to a maximum. So that's it. So this is just a regurgitation of the second derivative test. I don't think we need to restudy what the second derivative test is, or if you want to do the first derivative test, just to make a point. I'm not sure what point I was making. I was just thinking things like the quotient rule is useless to me, and the second derivative test is useless to me. But maybe in high-dimensional spaces, if I wanted to check things, then I wouldn't know how to apply that first derivative test because it's not a one-dimensional problem. And that's what my teacher could have said to me, is that only works in 1D. So what would you do in high D? Take the Hessian and check the eigenvalues. Make sure they're all negative. And what does that mean geometrically? It means that your function is peaking like that. So if all your eigenvalues are positive, the function has a minimum in there. It flips everything upside down. So if you want to kind of see that, if you just look at a normal model, if you look at e to the minus x minus mu, I'll just write it down like this in a high-dimensional example, transpose sigma inverse x minus mu right here. There's a half in here. It doesn't change where the optima are. If I took a log over this, basically it just gets rid of that thing right there. So we can get rid of that and we're just left with this function. And maybe you can see geometrically what this function looks like. It's an upside down parabola. How do I know? This is positive definite. So here's a fact. If I can factorize my matrix into two common things where I'm just transposing something into each other, so that's a Cholesky decomposition. And if you can do that, that is the definition of positive definiteness. It's kind of like positiveness for a scalar. Basically means I can take a square root over the top and nothing goes wrong. So if I can factorize it into two common things that I multiply into each other, it's like thinking about square roots in some sense. So if this is positive definite right here, sigma's positive definite, all positive eigenvalues. If I can factorize it like that, it's still positive definite. And if I throw the negative sign in front of it, it flips everything into negative definiteness. So if you're good with linear algebra, that would be maybe what you're thinking about. So in the exponential family, all the distributions kind of look like this. So if you're working in the exponential family, then you just need to take a derivative. Set it equal to 0 and solve. So another beauty of the exponential family is that things are well behaved and you get point estimators from your MLE that are well behaved. Does that kind of make sense? So that's max likelihoods. Let me say a little bit about Bayes. Very similar. So let's just look at this example that we studied a long time ago. This is the very beginning of class, and you might want to remind yourself on some of the estimators that we wrote down and talked about. This code is still online, so you can double check that. But if you recall, this problem, uniform, 0 to theta, right here, the max of the x's, I'll say xn, this was the MLE. Drawing a picture again, the likelihood function is going down and it's bounded by the max order statistic, xn, in braces. So the likelihood function for this, it's just that, but what is this thing? It's 1 over theta raised to the n, and I have an indicator function that xn less than or equal to theta, so theta is bigger than this maximum. That's what that says. So taking a derivative, setting it equal to 0 won't help you. The maximum likelihood estimator is this. We've already looked at this. It's a pretty good estimator. It's always biased. So it always lives to the left-hand side of theta. And that makes it a little bit undesirable because you don't have data on the right and left-hand side of things, so which gives information. So the Bayes answer that we came up with was a scale multiplier of this, some positive number that pulled it over to the right a little bit. And depending on how you invoke the criterions, and again, we need decision theory to write down what the criterions are, would define how good your estimator is in the first place. So Josiah's estimator was a scale multiplier of this, and it optimized something, and we'll talk about that in a week or two, what it was actually optimizing. And then the other Bayes answers that I gave you 2 other ones. One of them was able to minimize MSE. I didn't tell you that necessarily, but it brought down the bias squared plus the variance. And we'll work through that in a couple of weeks' time. And I gave you another estimator that was unbiased. So it didn't minimize the variance, but it was unbiased, and maybe that seemed desirable. Or maybe you want to take into account both those things. We'll come back around to this, but my point is that the Bayesian answer is probably a scaled version of the MLER's answer. And you can add some additional criterions to what you're trying to do. So I can invoke some criterions based off of maybe some objective criterion, what I'm trying to optimize in the first place. So I'm not going to say too much more about that until we get into decision theory. Any questions before we move forward? Okay, so it really doesn't matter how we come up with estimators. Maybe at the end of the day it matters to us, but how we compare the performance of those estimators will matter to everybody. Okay. So there's no magic wand out there that says you're going to have a technique that always guarantees you the best estimator on every problem. There might be criteria that we can use to say this estimator is best in some sense for a particular problem. But we're going to have to get more specific. Okay. Try not to give you anything too terribly complicated if I'm having you work through an MLE. I don't want to test you on all of that stuff they already tested you on in calculus class. Okay, finite mixture models. So this is just a recap. Finite, and I'll say additive mixture models. There are scale mixture models. There's other types of ways you can mix over things. So I'll just remind us that a t-distribution is a scale mixture of a normal with chi-squared distribution. That's what you learned in your first homework problem. You're able to derive a t-distribution, a t's density, by taking the variance and letting it be chi-squared distributed. So in averaging over that. So that's a scale mixture model. There's other scale mixture models out there, so I'll tell you this. A Poisson distribution is a counting model. It counts things between 0 and infinity. You can mix over lambda in a Poisson. So if I mix over lambda with a gamma distribution, and I let that be gamma distributed, you induce a different distribution. Does anybody know what distribution that is? It's a negative binomial, is what you get. So keep in mind, binomial model, or Poisson model has the mean is equal to the variance. So a negative binomial always has the variance bigger than the mean. So it's over dispersed. And you get that by adding more variability into the process. So that's kind of cool. So scale mixture models will always increase the variability on something. So if you don't like these criteria, you can mix over things in a hierarchical manner and create new distributions. I do that all the time. So when I get real data sets that don't come with models, I start off with simple things, like maybe if it's continuous or something, and I make a plot and it looks like kind of like a normal distribution. I'll say maybe it's normal. And then I do something with it. I fit a regression model to something, and then I figure out the tails are heavier. So then I mix over the variance parameter. Something like that, and I blow out the tails, and it turns it into a t-distribution. So I have control over that. And do the same thing with any distribution. Okay, finite additive mixture models look like this. So f of x is equal to the sum, k goes from 1 to cap k. So this is finite. That's where the finite part comes from. I've got these mixing weights. I'll call them the mixture weights. And then I have the distribution for each mixture component. F of x given some parameters that change depending on which group I'm in. So this is the actual mixture component. You might think of this as groups or groups. Sometimes people think of this as clustering. So if I'm grouping the thing into these different components, then I'm clustering. So this is equivalent to unsupervised learning if you were taking a class outside of the stat department. So regression is supervised learning. You get the y's. Here we just have x's. So we're trying to figure out what is the structure of all these things. So it's a clustering problem. I like to think of this as model-based clustering, where I'm explicit about what the parametric form of these clusters are. So pi k's sum up to 1, and all of these are positive. You can verify this is a distribution by integrating over it. If you integrate over these density functions, they integrate to 1. So once I integrate over that, that's 1, and then these things sum up to 1. So it's a proper distribution. So a Gaussian additive mixture model just has these components, and they look like this. F of x given theta k. These theta k's are just going to be your mu's and the sigmas, whatever your underlying parameters are. And I could write down everything like this. This is at least in the 1D case. This could be higher dimensional as well, but I'll just write down 1D for today. E to the minus 1/2, I'll say x minus mu k squared over sigma k squared. So they're just Gaussians. To sample from these, you can just refer back to that bootstrap code that we did a long time ago. So the distributions that we invoked for that code was a 3-component version of this. So we had some distribution that looked like this. 1, 2, 3. So cap k is equal to 3. Everything might look like this, or this is centered somewhere, this is centered somewhere else. This is centered somewhere else. And they might have different standard deviations attributed to them. So this is sigma 1, sigma 2, sigma 3. So, and what you get to see is not this distribution, but when you sample from this a bunch of times, where how would you sample from it? I would take a k-dimensional coin with probability weights pi 1 through pi k, and I would give it a flip. And I would see which side I landed on. And I could add labels to all of those, so 1 through cap k. And then I would sample from the corresponding distribution. So I sample that k-dimensional coin, we'll write this down next time, and we'll start with this. And then I sample from the underlying distribution. So 2 different steps. What I get to see is a histogram approximation to all of this. Let me just write down these 2 steps just real quickly. And we'll start out with this next time. Again, this is all reviewed. So step 1 is I'm going to take something, I'm going to call it ZI. This is going to come from a multinomial distribution. So binomial is a multinomial with 2 sides to the coin. This is like one of those Dungeons and Dragons dice. Jake, could you bring me one of those tomorrow?
Yeah, I have a D20.
Yeah, bring that in. We'll have a look at it. So, cap K. So I flip that coin right there, and then what I do, I'm going to say this is equal to some number K. K is going to be between 1 and cap K. And then I sample the xi corresponding to this. And this is going to come from my corresponding distribution. If we were in the normal class of things, I would just take this right here, where this k right here is going to be those k's, these values. And then I get a x out of there. So this is mu k sigma k. So what we normally get to see is just the x's, just these values right here, this histogram. If you got to actually see what the labels are, estimation is really easy. We'll go through that next time. Then I'm going to show you what to do if we take the z's away. And you have to co-estimate what the z's are and estimate the mu's simultaneously. And they have something to do with each other. So how do you do that estimation? So that's what we'll be going through for the next lecture or two. Okay, that's it for now, you guys. Let me just hand back up a few homeworks. Okay, welcome back everybody. We're going to study the EM algorithm in our example that we're going to use to kind of go through everything is finite mixture models. Saying that the EM algorithm is a general algorithm. and it can be used in a lot of different contexts. Has anybody ever heard the term variational Bayes? Okay, we need more people doing that in colloquium, I guess. It kind of went through its, you know, I would say its popularity, you know. So about 10 years ago, if I went to Bayes conferences, there would be a trade war on variational Bayes implementations. So it's always like that. You know, you go to a conference, a specialty conference, not like JSM that's like a free-for-all, you know, the Wild West. But, you know, something that's more specific and tailored. And you'll start seeing people are always like jumping into something. There's fashion to it all. Interestingly, the variational Bayes algorithm is a approximation to a posterior distribution, so it's not like just likelihood times prior, but it's an approximation to that function that factorizes in a nice way. So approximation, and then they run EM on top of it. And they say a lot of stuff about it, lots of math, lots of measure theory. But it really is just an approximate model with the EM algorithm attached to it. So you can remember that for the future, so when you do encounter this, you can go, oh, it's an approximation with this algo that I studied in inference class. So this is an oldie but a goodie. And I've seen this algorithm come into fashion many times over. I will say that things like Google Chat, so when you're sitting there and you start speaking, and all of a sudden the camera flips over to you, so if you have like one of those 360 cameras in a conference room, you start speaking, it figures out there's a cluster that's louder than other clusters over in this region of the space, and I'm going to zoom in there. So what it's really doing is it's doing a mixture model approximation and figuring out which cluster things live in. Okay, so it's very much like a finite mixture model thing. Saying that, those sort of chat services with the video cameras, they don't always know exactly how many people are in the room, so it has to approximate that as well. And so it doesn't know what cap K is in my notation. And so it has to do something slightly more sophisticated. How does it do it? Variational Bayes. So it actually does a Dirichlet process model, and it runs the EM algorithm over the top to be really fast. So I will say this. One of my favorite algorithms is MCMC, Markov Chain Monte Carlo, that helps us to get the posterior distribution of parameters in an underlying model. Sometimes that's overkill. Knowing all the joint uncertainties about things, sometimes you just need to make a decision. And so sometimes optimizing something or maximizing something, you're not getting as complete of an answer, but you can do it quickly. And so that's what things like Google Chat are doing. So it's doing this sort of optimization algorithm on a Bayesian model, and it's shortcutting a step because it doesn't want all the joint uncertainty. So you probably wouldn't want to see like a blurry vision of person one over here and person two and showing the mixture of images. That probably wouldn't be a very good thing to do. It probably wouldn't be a good thing to do to say, I'm 35% certain it's this person, and I'm 75% certain it's this person that's talking in the other side of the room because there's an echo. So sometimes you just want something to make a decision for you. Saying that, automated decisions and putting all of your answer in one spot sometimes can lead you to wrong answers. So sometimes there are good reasons to quantify all the uncertainty about things. I will say the implementation we're going to do, it does a little bit of both of those things. And we'll talk about the full-blown Bayesian answer, and then we'll talk about an optimal answer in some sense. Instead of giving you all the joint uncertainties, I give you an answer. So let's just write this down again. So what we're going to study specifically is this finite mixture model. So it looks something like this. K goes from 1 to cap K. I've got some mixture components with some weights attached to them. These are the weights. This is my mixture component. And I've got some model parameters in here. And I'm going to call this f of x. This is my overall distribution. Now I dropped a little bit from the notation. Anything that models are conditional on over here, they're conditional on over here. Okay? So sometimes I'll just write things like this. xi is going to come from this thing right here. So this means xi's are distributed according to that, and they have some global distribution. And that global distribution is comprised of cap k components. So if maybe cap k was equal to 2, what we're talking about is something that looks like this. So 2 component model. When I actually go to work out the details for everything, and you can generalize this on your upcoming homework, I'll write it all out in a PDF for you. You will generalize cap k to bigger than 2. It should not be hard to do. If you can see what you're doing with cap k is equal to 2, you can see what is happening with arbitrary cap k. The formulas work out exactly the same. So I don't mind if you do what I call grad school induction. You work it out to cap k and you sit there and you go, yeah, it would work out the same for any cap k. So you pick 2, work it out, and then show how everything generalizes. I call it grad school induction, but it's like, yeah, that would generalize. So maybe a better version of grad school induction is you do it for cap k is equal to 2, do it for cap k is equal to 3, and then go, oh, of course it generalizes. So the idea is in real induction proofs, and you don't have to do it in here, is you show it for cap k is equal to 2, then you pick an arbitrary cap k, and then you show it for cap k plus 1. And so ultimately what you've done is you've generalized it to everything. That's not important if you're not that formal in this class. In your measure theory class, they'll make you go through that very formally. Okay, so this is what we're talking about. I really like models like this because it doesn't just show us about individual behavior, but it shows us about different group behavior. So if I were going to try to average across this and model everything with a normal distribution, I'd be averaging over the group uncertainties. And that might not be what you want. So it certainly make your life easier. You could maybe invoke the central limit theorem, maybe do delta method like we did early on, bootstrap or something like that, make everything easy and generalize things into global averages, but what we probably want are the group averages. So mu1 and mu2, and we probably want the group uncertainties, sigma 1 and sigma 2. So if these things were normally distributed, these two distributions, that would be the only thing that underlines those distributions. I will point out this doesn't have to be the same distribution for every component. They could be different distributions, but of course, if you're going to implement this, you're going to at least have to have some candidate choices in your code. It's not going to figure it out for you and say, no, it's not normal. Do you know anything about gammas? Or something like that. You would have to encode that and check over the multiple components. We'll make everything easy here, and we'll make sure that this is all normal. All of these will be normal. In our upcoming example, I'll say homework simulation study. So really, all you have to figure out if this is going to be a Gaussian mixture model. So let me just write this down, Gaussian. That means all of these are normal, and that means that these are just the group mean and the group standard deviation. So that's what the thetas are. And then these are the component probabilities. Probability of being in group K. So this is a clustering problem. This really is just clustering. We're just given X's. We're not building regression models. You could build clusters of regression models too and extend this to that sort of case. But that's not the way we're going to motivate this. But I like answers like this, you know, where it's like, give me the specific groups. So I really don't like answers that on average, you know, let's just say we're talking about a pharmaceutical thing or some dietary constraint. On average, this thing's going to kill you. Okay, great. Something will. Thank you for that. What does it have to do with me specifically or people that have my same conditions? So I want to know about things like that. So I think all of this is the future of statistics, is breaking things into like groups. I will kind of point out also, if you had distributions that looked really funky, maybe stuff like this that were really skewed, and you didn't know which distribution this was, you could say, instead of modeling this distribution, I don't know what it looks like. Maybe your ears look heavy-tailed or something like that. Maybe they're always constrained by 0. So maybe that's 0 right there, and you don't know how to model this. Then you might say, I'm going to not do this, but I'm going to assume that the error distribution is modeled by a finite mixture model. And so it turns out, if I have enough of these components right here, I can model almost anything that's smooth. And so we could probably write a proof about that. That if I have a smooth function, then I can model that smooth function by taking a collection of normal distributions and averaging over them. And that's what this does. So it's just averaging over a bunch of distributions. This would be considered what I would call a semi-parametric analysis on something. Some people call it a non-parametric analysis. I call it semi-parametric because there are underlying parameters in here. There's where all of these are centered. Saying that, you might not be interested in those. They might not have any meaning to you, what these groups are. Here in this illustration, they would have real physical meaning to you. In doing something like this, you would be just saying, I don't know what the distribution is, it's something smooth, and I'm going to use this mixture model as a proxy for modeling those errors. It turns out, usually you don't need a ton of components to do something like this, but maybe between 5 and 10. So, kind of a nice thing to do. So this is also the basis for what I would call semi-parametric analyses, but some people would call them non-parametric analyses. You could kind of imagine that for some arbitrarily complicated function, I could approximate it with a mixture of normal distributions, but there might be an arbitrary number of those distributions I have. So in terms of a process, it might be infinite dimensional, meaning the parameters that underlie some arbitrary process, there could be ultimately an infinite collection of these normal distributions that model things. That's where the term comes from. If there's a potentially infinite number of parameters, then we might, and we're not interested in those, then we might call it non-parametric. Keep in mind, this is very different from like the old school rank-based sort of stuff that people will call non-parametric. So this is a modern view of doing non-parametric analyses. So that's kind of cool. Might not assume that your errors are normally distributed, but rather some collection of normals. And the name of the game is to figure out what are the weights, how many components do you need to model all of this, and what are the underlying parameters. Josiah.
This is starting to remind me, and I might be confused here, like modeling a smooth curve with a bunch of kernel density.
Yeah, it's just like that. So kernel density estimation puts the same weight on everything. So it puts the same weight on every point, so it's a little bit easier to do, and then you smooth over everything. So it kind of has this sort of form. So it's like doing a kernel density estimation, but in high dimensions, those can be really rough to deal with. You can imagine your data points are fairly sparse. If I'm putting the same density on every point and smoothing over it, it might look rather jagged in high dimensional spaces. So the question is if you're doing kernel density estimation and you're using the same normal distribution for everything, the whole question is, so I would say this is going to be stacked right where you're, I'll just leave that as a mu just for notational purposes. But the name of the game is how do you pick the sigma in all of that? How much do you smooth over that stuff? And in certain regions of the space, you might want to pick different regions and do adaptation. I've never been good at this, and every time I try to do this in high dimensional spaces, I convince myself I'll never do this again. So it's kind of like building a histogram in high dimensional space. In fact, I would say it's exactly like building a histogram in high dimensional space. Histograms are putting mass on each data point, but instead of a Gaussian, you're putting a flat function. So this is kernel density estimator is a smoother version of a histogram. I do like them for visualizing things and illustrating things for people, but analysis-wise, I never really love them because of that sigma selection thing. It's called a bandwidth selection problem. It can be really tough. What do I mean by high dimension? The highest dimension I've ever been successful with this kernel density stuff is 7-dimensional, so which is wildly large to me. So I wouldn't even touch that over like 4 dimensions usually. This I could apply in maybe any dimensional space, and having that in there really helps out. So yeah, similar idea. So all these, after a while, you run out of ideas. It's just about how you combine the ideas in different ways. So yeah, good catch. This is the number of components. I'll say groups just to use a different word, but I'll go back and forth between saying components, groups, clusters, things like that. Okay, so that's what our finite mixture model looks like. When we work through everything, I'll just end up using cap k is equal to 2. We'll work through the specifics on Friday, and I'll do generalities today. So if you leave and you go, okay, I kind of get all the steps of the proof, but I need to see this in an example, I will work through those steps in an example, and then you'll kind of extend that example for your homework. Okay. So let me just remind us, if we're going to sample from a mixture model, we're going to do these 2 steps. And I'll say additive mixture model. I guess I don't need to say additive mixture model because you still kind of employ these 2 steps in any type of mixture model. A mixture model is a hierarchical model. So you're going to do step 1 is I'm going to sample from a multinomial distribution. And this is going to be k-dimensional. And it's going to have these underlying probabilities, pi 1 all the way to pi cap k. And I'm going to give myself some groups, so I'm going to sample zi from this. And the zi's are just some arbitrary labels. So this is going to be 1, 2, all the way to cap k. I don't care what you call these groups. You could call them red, green, blue. The ordering doesn't matter. But I don't have good notation for that. So basically, I'm just going to define my groups with this latent variable zi. Usually, we don't get to see it. But if I'm going to simulate everything, then I would need to do that. Jake, got dice?
I did not. I was not able to dig them out. I have regular 6-sided dice, but that's not all that exciting.
Yeah, I have those too. So anyway, now I think it's kind of funny. When I think about the D&D guys, I gave this a lot of thought last night. Got to think about something. Those D&D guys, and we were having this conversation outside my office the other day. Now, correct me if I'm wrong, because I've played the game like once when I was like 6 and decided I didn't like the game. So, but I like the idea of the game. So, you get a character. You are a character in a Dungeons and Dragons game, and your character has certain attributes. So maybe like how stealthy they are, how strong they are, they have special powers or something like that. And they have numbers, right?
Yeah.
Attached to it. So maybe between 0 and 100, or?
I have no idea on the range of that. My experience is about the same as yours with actually playing the game.
Pretend you know.
Okay,
So
yeah, it's definitely between
there's some
0
number.
and 100.
It's between 0 and something. So it's kind of arbitrary in some sense, at least theoretically. And so at the end of the day, you end up saying, I'm going to take my character and I'm going to make them go do something. And whether or not they're successful in doing that or not, and what the penalty is, comes down to a dice roll. So you roll the dice, and depending on how many players you have at the table and what your attribute level is, determines which dice you grab, right? So basically, you just want things proportional to your attribute level. So whether or not you're going to be successful. Is that right?
Sounds about right.
That's an absolutely yes, right?
I think a lot of the time it comes down to whoever you're playing with. I think there's the dungeon master makes all of the decisions on what you do and don't roll.
Okay.
But I have no idea, really. Which I'm going to translate to, I know everything about this game, and you're exactly right.
That's what most rational dungeon masters will do. So what I'm curious about is, let's say people have attribute levels of like 7.2, and somebody else has an attribute level of 8.14 or something like that. All of a sudden you would need this new customized dice to deal with the problem. And so instead of doing all of that, I think the dungeon master will say, you have to round everything arbitrarily. Let's round and make it approximately something that we can work with the dice at hand. Is that about what happens?
I think that they don't use, I think they only use whole numbers.
Okay, so they use whole numbers because of this.
Yeah.
So that's the rounding thing that I'm talking
exactly.
about. Exactly. So they won't do 8.3, so they'll say round to 9, and so that creates an approximation to everything. And so I think modern day players say, forget about all that approximation stuff, and let's just go to our computer. And they probably have an app on their phone or on their computer, and they can simulate through any proportions or anything like that. Is that about right?
That's exactly right.
Okay, so they don't even do the dice thing anymore because it's way too approximate. I want to make a point that all that asymptotic stuff that we see, a lot of times we say, oh, something is asymptotically chi-squared. They're kind of like playing like the dumb dungeon master and saying, let's round and only use whole numbers and do something that we know is not quite right but good enough. When instead of using some approximate distribution, let's say maybe that's not quite chi-squared for a certain sample size, you could do this thing and come up with a much, much more refined approximation of some error distribution. So my point is that I think everybody should do this sort of stuff instead of making super clumsy approximations and hoping maybe n is big enough. So I think this stuff has a lot of utilities. I'll say probably about 25% of my applied papers do something like this in there. And if you bring this stuff over to fields that is brand new and they haven't seen it before, you'll win lots of awards for doing things that people already know how to do in this field, which is kind of cool. So definitely bring this to your fields if you're not in statistics or if you're working with non-statisticians. Okay. So 2 steps. First, I just flip this coin. I can put any probabilities into this. I'm not constrained to the dungeon master's rules. So I can write these down to any precision I want. So that's the group label. So group label. And then what I'm going to do is I'm going to sample the xi's. This is what I actually get to observe. And they come from the individual components. And I'll just write down zi right down here. So that's one of these values of between 1 and cap k. So x given theta zi. So that's some number that identifies the label. I'm going to be a little bit more specific right here, and I'm going to say Zi is equal to K. So I'm going to build that into my notation. And so same thing, it's a little bit superfluous because I already know what Zi is. I could write down that that's some number K right there, whatever number it turns into. And I could just write all that stuff in. It's all the same information. What I'm probably setting up you for is being able to do inference on Zi by putting it into the model and explicitly labeling it as a parameter. So if this looks like I'm about to do something Bayesian, I probably will. So upgrade that and try to infer what the Zi's are in the process. We'll come back to that on Friday, and I'm going to reintroduce this notation and be explicit about that. But that'll make things real easy for us so we can apply Bayes' theorem. At least I think of it as Bayes' theorem, what people do, but there is some controversy as to whether or not I should call it Bayes. But I just mean that likelihood times function thing. Whether or not you call that Bayes or not, I don't really want to argue about, but I tend to think of that as Bayes. So we'll come back around to that, and we'll ask, is this a Bayesian algorithm, or at least semi-Bayesian? I think the answer has to be yes, if you want to think about it that way. Okay. I will point out, non-Bayesians also use this algorithm, and they like to say it a little bit differently, so I'll say what they say. I'll tell you the two different versions of how people phrase the exact same thing. Okay, so this is the idea. You've seen this before. Jay Young took us through this. Our Bootstrap code implemented this early in the semester, and we'll re-simulate this next time. So pull out my code and do some simulation a little bit later. This usually is not observed, so the labels. If you observe this, it's called supervised learning. I get to know the groups, I get to know the labels on everything. If you don't get to see this, this is called unsupervised learning. So you have to figure out from the structure of the data what are the groups in everything. There is information. If I knew what the mu's were, of course we don't, we'll need to infer them, but if I did know what the mu's are, if they were right here and this was my underlying picture, if I saw a data point right here, let's say this was xi, I'd probably think that's attributed to group 1. So how would I know? It's closer to its mean, and I'm accounting for the standard deviation, so it kind of seems to fit into this distribution better than it does into that. Of course, there's some probability that it's in this distribution as well, but it's vacuously small compared to being in group 1. So there is information in here, and we'll be able to figure out probability statements for which group each data point is in. What we're going to be doing in the EM algorithm is updating what we think the mu's and the sigmas are, and then we update the groups, just like the picture that I'm drawing. Then I take what I think the group labels are at that step, I'm going to update the model parameters, and then I iterate the other way and I update the groups. And I keep doing this over and over again, and with some luck, everything converges to the truth. So that's the name of the game in the algorithm. Let me write down specifically, actually, before we write down the algorithm, let me just say what we would do if we did get to see the Zi's. So, if we observe Zi's, so for every corresponding xi point, I knew which group it came from. I know that it has a common mean and a common variance. So that would be pretty easy. So let me just give us some notation. So I'm going to say the number of Zi's that are equal to some number k, I'm going to say is nk. So what I'm going to do is I'm going to look over my whole collection of Z's, Z1 all the way up to however many of these I've sampled in the first place, I'll say it's n. So I'm going to repeat this n times. So 4, I goes from 1 to cap n. I'll have n xi's, and n corresponding zi's, the labels. So I can count up how many of these that I have of each label. So what I'm going to do is I'm going to look at how many of the zi's are equal to a 1, and I'm just going to count them all up. Okay, and then I'm going to collect also the corresponding xi's. So I'm going to say xk, and just make up some notation here. This is going to be a collection. This is going to be the xi's. So what this means is I'm going to make a set of something, and I'm going to condition on something. So this notation is the same notation I use for distributions. These are the conditions, and I'm going to create a set of things that follow some conditions. So that's the typical notation. So I'm going to look for the collection of xi's such that zi is equal to k. So these are all the corresponding xi's such that zi is equal to k. Xi's such that the zi is equal to k, and this is going to be for all of my i's, I goes from 1 to n. So that's what my notation expresses. So I can collect all of the x's corresponding for all the different groups. So, and I would have, if I had some cap k number of things, I'd have cap k of those, and I'd have cap k collections of my xi's. And they don't all have to be the same size. So how many points I get in there. Of course, the number of points that I see in each group has something to do with the probability of being in that group. So groups with higher probabilities, I would see more points in on average. Okay, so this is my notation here. We'll come back and we'll use this notation a little bit later. But if I gave you this, and I was able to break this data set into cap k groups, how would I estimate mu k and sigma k? I'll say sigma squared k. What would you pick? So somebody walks into your office, says, I've got this really hard problem. I've got groups. Nobody ever told me what to do with groups. I do have all the labels. And what I would like to know, I know everything's Gaussian. I'd never trust anybody on any of this stuff. If they walked in and started telling me things, I'd probably check. But let's say we trust them. They say it's Gaussian, and they've already done all the hard work and broken everything into groups. They go, I need some estimates for mu and for sigma. Can you please help me? What would you tell them? I need an elementary school for this. I bet I could go to like a 6th grader and they could give me an answer at least for mu is. I don't know if they know what sigma is.
X bar k?
X bar k. Yeah. So X bar k. I'll leave it with that same notation. This is just the sum of the, I'll just say X k's. These are just the x's in this group. So I'll just follow that same notation right here. This is going to go, I'll just introduce a new dummy variable, j. J goes from 1 to nk, the group size, and I divide by nk. So I just give them the group average. Piece of cake. Similar thing here. Give them some point estimator. xj k minus x bar k. Square that thing out and normalize. Maybe if it's somebody coming in, maybe they like the unbiased argument. Again, I always do that. So we'll talk about that a little bit later. Let's just think about this. Like, why do we do -1 again? Let's think about what they do in Stat 101. I was there. I remember this, you know, people messing with me. Why do they do this? It's the unbiased. So this is S squared. This is a nice property, I guess. This is sigma k, this is squared right here. So it's unbiased, so okay, great. That's what they tell you. It's unbiased, okay, I'm buying that, I like it. And then if they say you want to estimate this thing instead, they say take the square root of it. What does that do? Is it still unbiased? What's that?
We got the inequality now, density inequality, because like it's not a linear function.
So what does that mean?
So the expectations aren't equal.
It's not unbiased. So this is not an unbiased estimator. This is still not a bad estimator. So this is not unbiased. So it kind of defeats the whole purpose of the whole argument. Why did they tell you to take the square root? So you can put it on the same unit scale and you can think about it. So, but didn't we just give a biased answer back? So I'd rather just have a better answer. In the first place, it turns out this one right here is the MLE if I square that out. And what we'll learn later, if I take the square root of that, remove that, that's the MLE of the redefined problem, because MLEs are transformation invariant. So I can just plug them into the same function. We'll come back to that proof next week. Okay, so just aside, do whatever you want. If we're actually quibbling about this in terms of an application, I'm going to say, you need more data. So this really makes a big difference. Okay. So easy problem. I just estimate everything. I would know which data points are in here. I'd already have everything labeled. I can grab those data points and do this sort of thing. You might say, if I didn't know the z's, maybe you draw the histogram and you say, well, I draw the histogram. I definitely think everything over to this side came from this group, and everything from this side came from that group. But then the big question mark is, what do you do about the overlap between things? And so, and if you just tried to do it by eye, you'd probably mess it all up. In high-dimensional spaces, you wouldn't have any hope of doing any of this. And so what we need to do is co-infer in some sense what the zi's are. Okay. Let's go into the EM algorithm. That's what the EM algorithm will solve for us. We don't get to know what the z's are. We do get to see the xi's, so we have something that's missing from us. I could use other words like latent. We don't get to observe it, unobservables, things of that nature. But it's part of the problem. I needed to express what the process is. It's part of the process. So here's our goal. This is the goal, at least that EM solves. So I'll say this is EM's goal. So what they want to do is they want to maximize some function over theta. They're going to be interested in these thetas. So our thetas for our problem are the underlying model parameters. I'll also say that the pi k's are also part of our thetas. We're going to want to infer those as well. So I have some thetas that I want to infer. I get to observe data, and I have these latent variables that I need to deal with. So there's three things. Thetas, parameters I'm interested in, latent variable, and data. Okay, so latent data, I would say, in some sense. So data I get to observe, and then I have all the model parameters. That and those. So three things that we need to keep track of. Okay, so I want to maximize over the model parameters. That'd be nice if I just had this function. How do I get this function in the first place? I need to integrate over things. I'm going to change my notation ever so slightly to match what most books have and to make this just a little bit more general. So I'm going to say this is going to be integral of f theta psi right here. This is going to be my latent stuff. So in our example, this is going to be the z's. I just want to break you out of thinking about it as a very specific algorithm tailored to this finite mixture thing. You can use this in any context when you have something missing in your model. Whether or not it's a latent parameter that you never get to see, or latent data, however you like to think about that. ZI, certainly not a model parameter, but it's something. So we'll give it a name. So it could be that in a problem like this, something you don't get to see, the mixture component, but it could also be missing data. So if you're working at the Census Bureau and you're collecting data and you want to analyze it, I assure you, you'll see a lot of missing entries in there. And so you could do the exact same thing, and people will run things like the EM algorithm on missing data sets. And they'll be trying to deal with this parameter right here and do something with the missing stuff. Data can be missing for any number of 3 different reasons. It could be missing completely at random. It could be missing because of the response that you're trying to measure, or it could be missing depending on the person's attributes. So it could be missing because of the Y's, it could be missing because of the X's, or it could just be missing totally at random. Usually things are missing because of the response, which is the hardest case of missingness. So they want to know something about some phenomena. So for instance, let's say people are trying to measure risky behavior, and they come to Jared and they say, Jared, we're trying to measure risky behavior. Please tell us how many times we've taken heroin. And you go, I'm not going to answer that. There's that one time. It's a bad day. So obviously, that probably never happened. And we can't distinguish those things. So you might be disgusted by the question, how dare you are even asking me in the first place? It could be because the answer was yes. You didn't answer the thing. So that's just an example of why things could be missing. It could just be the questionnaire is just too long, and I just stopped answering it after some point. So you would have to model all those mechanisms of missingness. Okay, so this is just general notation for whatever's missing. And I'm going to say this is all conditional on data. And instead of writing data, I'll just write D right here. These are going to be my XI's in the model that we're studying. So that's the observable, the XI's that we get to see, the X's right there. These are the Z's, and these are the model parameters that we're after, the mu's and the sigmas. So let me just write that down. These will be mu k, sigma k, and the pi k's. K goes from 1 to cap k. So all of my model parameters. So for our specific problem, that's what all the notation means. This function right here could be a likelihood function, it could be a posterior distribution, it could be anything like that. This isn't specific necessarily to a probability distribution or a Bayesian posterior or a likelihood, but that's where people usually use this. So usually, if you're using EM, thinking about expectations, you're thinking about probability models. So, but I will say this will work for any arbitrary function as well. And what we're going to do is we're going to integrate over psi, and I'm going to take the maximum over here. So this integral right here is what I'm calling f theta. So cap f theta is the integral where I've integrated over my missing stuff. So that's our goal. That's what EM algorithm sets out to solve. So if you just want to think about this a little bit more, what they're doing is they're averaging over the missing stuff. That's what the integration means. So average out the missing stuff and then maximize the model parameters. So EM is solving both of those operations. So 2 different things. Let me just ask you, if this is a likelihood function right here, can I integrate over psi? There's 2 possible answers to this question. This is a dichotomous question. Josiah said, anybody want to argue? You can. I could physically do it. If it was an integratable function, I could just do it. So the argument might be it's not a random variable. The only way you can start integrating over that is if you're a Bayesian and you've upgraded it to a random variable and you have some prior. So somebody would say, well, I did the integral, it works out fine. And you might say, well, that means your prior was 1. So I guess what we could do is sidestep that conversation and say, if you were adhering to the rules of probability, you just came up with this improper prior sort of Bayesian analysis and didn't tell us about it. So this is the step that most people will argue about and say, this is Bayesian right here. This whole integration, and this is a posterior distribution. If you like to think about it, it's a likelihood. You're not allowed to integrate over parameters in your likelihood because you haven't worked through that Jacobian calculation and stretched the space and said what everything means properly. So I would say this part of the step is kind of Bayesian, and then we're doing something that everybody does. They maximize. So maybe we're looking, if I'm thinking about a Bayesian estimate, I'm averaging over the missing stuff, and then I'm giving you your maximum a posteriori estimate on top of it. So that's one way to think about it. But I would say this step feels Bayesian to me. So you will hear a lot of people argue about this, and I found it to be totally unproductive. So it can be fun. Okay, let me just tell you what the algorithm is, and then next time we'll come in and we'll write down a proof to show you that we actually converge to the answer here. So here's the EM algorithm. It's going to be an iterative algorithm that iterates over 2 steps. So this is going to run in some for loop, and I'll just say that's big. So this is something big enough to assure that you've converged to the answer. So if you run your algorithm twice, and you're coming up with 2 different answers, up to some decimal place, and that's not good enough for you, you want the answers to be same to that decimal place, you'd make this number bigger. You'd run it over and over and over again until you were satisfied with the precision of your algorithm. So anything you want to report back, make sure that's converged, and just crank this thing up. So step 1 is the E step. It's an expectation step, and step 2 is the M step, the maximization step. So you can tell the statistician made this. So it tells you exactly what it is. Very important. Okay, here's what the E step looks like. We're going to have to talk about this step because it can be a little bit confusing at first. But it looks like this. You form this function. And I'm going to condition on something. These are going to be my previous guesses. So this is an iterative algorithm. So this is my previous step, what I think the model parameters are, your thetas. So the thetas are the pi's, the mu's, and the sigma in the finite mixture model. And how you get this is you work through this calculation. Expectation of the logarithm, and I'm going to say the word likelihood, if you don't mind. So log likelihood, theta, psi, given our data. So I work through that right there. I need to be specific as to what expectation this is. So this is going to be the expectation over theta. Nope. This is going to be the expectation of psi given theta where we were last time. So there's no theta t's in here right here. So it's coming through what we're averaging over. I want to be real specific. Most books will give you this notation. Anywhere you see anything, make sure you've conditioned on the data. So everything is conditional on the data. At every step, you get to see the data, you get to look at it. So most books will leave this out of their notation, and it bothers me completely. So this is going to be an integral. If I'm thinking about psi as something continuous, Obviously, in our examples, the missing thing is discrete. So just we'll replace later on our integral sign with a summation sign. I just like to think of everything as continuous as my primitive. Okay, so this is just a logarithm of the likelihood function, if you will, conditional on data times my distribution on the missing stuff. This might be confusing at first, but we'll come back around to what is this distribution. But it's ultimately modeling our missing stuff. So d psi right here, and we're going to integrate over the whole universe of psi. So this is not exactly what we wrote down in the first place, what we're integrating over, but it has something to do with it. Okay, so what we're actually doing is we're invoking the fixed point theorem by doing this so that we can come up with an iterative algorithm to update these theta t's. So I'll say more about that next time. Our second step is just this, update the theta t, and what we're going to do is we're just going to take our arg maximum over theta of this function q. So this step is relatively straightforward and easy to understand. Let's just think about what we've done. We've done an integral where we've integrated over psi, that's what this expectation is. And up here, in terms of our goals, we integrated over psi. And then later on, we maximized over theta. So we probably want the arc maximizer of all of this. They're the same problems. If you can maximize, they can tell you the point in which you maximize. So this looks like slightly different steps for doing everything, but at least they look similar to each other. I've integrated over the right thing, so there's some hope that this algorithm works. We will work through this integral for our specific problem next time or on Monday. We'll at least get through this by Monday, so that you can at least see exactly what this integral is. What I'll point out to you for the problem that we're studying, we can write this down in closed form. We'll have a closed form solution to this. We'll have the answer to this. We don't need to take the expectation and do this step over and over again. So what we're going to do is we're going to be able to solve this in closed form. We can do this outside of the loop and just have that function, and then we'll just iteratively maximize over everything. So the algorithm that you're going to code up is really just this step because we can just do this mathematically. Sometimes people will bury this inside of the loop just because they won't have a closed form and they need to come up with an approximation at every step. So this could be approximate. So could be and Monte Carlo MC approximation. Also, this maximization doesn't need to be precise. It just needs to increase everything at every step. In all maximization algorithms work that way. It doesn't mean that you go all the way to the top of the hill in one step. There's probably some theorem out there that says, as long as I'm making progress up the hill, I will eventually reach the top. So where else would you wind up if you keep going up? So I thought about this. One year I was in Yosemite climbing up Half Dome, and I thought, so tired. It's carrying too much stuff, too much water for everybody. And I thought about this algorithm. How do I reach the top? Just one foot in front of the other. Just keep marching, make progress. If I need to zigzag to cut the grade, I'll do that. But eventually we'll reach the top. So this doesn't need to be precise. We'll come back next time and show you that this algorithm right here accomplishes that goal. It's not obvious. It's not in the book. I know one book that has a decent proof in there, but I'll give you my version of this proof that shows that it works. This was when I was in first year of grad school. When I saw this, I was like, I can code it up, but I really don't get it. I can see that I'm doing an integration with respect to psi and maximization over theta, but it does not look exactly like that. So let's come back next time, fill in the details of the proof, and then after we get through that, we'll work through this Q function specifically for the mixture model. Okay, that's it for now, you guys.